How do celestial objects form in the cosmos? In standard astronomy, at all cosmological scales, from the condensation of dirty snowball comets in a primordial nebular cloud, to the slow, gradual accretion of planets forming in a disk about a star, to the gravitational collapse and compression of clumps of gas and dust in molecular clouds leading to the formation of stars. For generations, astronomers have believed that gravitational processes, and only gravitational processes, govern the formation of the objects we see throughout the cosmos. I've now spent well over a decade composing video presentations which juxtapose the theoretical predictions and explanations of standard astronomy versus those of plasma cosmology and the electric universe. In our electric universe, it is not gravitational collapse, collisions, and accretion that create planets, stars, nor any celestial objects, but rather it is the experimentally verified plasma phenomena of Birkeland currents and the electromagnetic Bennett pinch, or the Z-pinch. Today I'd like to revive the approach I used on Space News and focus on a few recent science headlines that should again provide wonderful opportunities for such a juxtaposition. Firstly, scientists studying data from the European Southern Observatory's ALMA telescope have discovered evidence of shockingly early planet formation in the disk about a so-called protostar. A PhD candidate at Yale University named Dr. Cheng-Han Hsieh made the discovery in an effort to determine at how early a stage planet formation begins about a star. Describing his research, he stated, "ALMA's early observations of young protoplanetary disks have revealed many beautiful rings and gaps, possible formation sites of planets. I wondered when these rings and gaps started to appear in the disks." What Dr. Hsieh found has stunned the astronomical community. As described in a piece on Universe Today, the ALMA images, quote, show class 0 and class 1 disks. The classes refer to the age of the stars that host the disks. In fact, at these young ages, they're not even called stars. They're called young stellar objects, or YSOs. A class 2 YSO is a protostar with a visible photosphere, but the new images show YSOs and disks that are class 0 and class 1. At these young ages, the YSOs are still in the collapsing and formation stages. A YSO is only a class 0 object for about 10,000 years, and a class 1 object for a few 100,000 years. So finding rings and gaps in the disks around these extremely young stellar objects is a surprising development, to say the least. If planets are forming this early in a solar system's life, it challenges our entire understanding of how planets form. Dr. Hsieh acknowledges that the, quote, rings and gaps observed in these disks may not actually represent planets, but in standard theory might be caused by instabilities, such as gravitational perturbations. Regardless, 2 points in this piece stand out to me with stunning clarity. Number 1, while astronomers only entertain 2 possible theories of planet formation, core accretion and gravitational instability in a protoplanetary disk, both of which require a vast expanse of time after a star's formation for a planet to form, the electric universe has always predicted that both planet and star formation happen in a cosmic eye blink. Countless times, we've discussed the filamentary networks along which stars have been imaged forming in molecular clouds. As stated many times previously, the remarkably constant width of the filaments, a gravitational impossibility, is the hallmark of electric currents. In the electric universe theory of planet and star formation, some planets will form along the same Birkeland current filaments as their parent stars, with other rocky planets likely being ejected from the cores of gas giants. It must also be noted that the electric universe offers an alternative diagram to the standard Hertzsprung-Russell diagram, which explains the observable stellar phenomena in terms of electric current density. And critically, in the EU diagram, it is not possible to tell the age of a star. Supernovas are not the result of stars running out of nuclear fuel and gravitationally collapsing, but rather they are catastrophic electrical discharges along the electrical circuitry connecting the star to the larger galaxy. Wal Thornhill's peer-reviewed scientific paper on this subject, entitled The Z-Pinch Morphology of Supernova 1987A and Electric Stars, was published in IEEE Transactions on Plasma Science in 2007. Evidence for so-called early planet formation has been accumulating for some time. For years, astronomers have been puzzled by the lack of dust in the so-called mature disks of stars in the Milky Way galaxy. As we reported in 2018, astronomers using ALMA attempted to determine how much material is present in the disks about stars that are thought to be only 1 to 3 million years old. When they compared their estimates to the masses of star systems that have fully formed planets, they realized that the so-called young star systems did not have enough matter in their disks to eventually form planets. According to a 2020 paper published in the journal Astronomy and Astrophysics, the answer to the puzzle is that planet formation happens much more rapidly than astronomers have ever considered. The lead author of the paper stated, "We need to look earlier instead of looking for missing mass." In fact, the team concluded that planet formation has already begun around stars that are thought to be only 100,000 years old. The co-author of the paper stated, "The implication of this discovery is profound. For decades, we've thought that planet formation should happen during the protoplanetary disk phase. But by pushing the beginning stage of planet formation back, we have to rethink what the birthplace of planets actually look like." Recent scientific discoveries have offered a similar basis to rethink the timescale of star formation. Consider the Herschel telescope image on your screen of a stellar nursery in the aptly named Snake Nebula, where a number of stars are forming along the filament, and the stars themselves break up along a cylinder. This is in stark contrast to gravitational theory, which predicts that a center of mass exists toward which all of the surrounding material in a nebular cloud tends to move and to congregate to eventually form a star. In 2014, scientists studying the Snake Nebula discovered several, quote, surprising things about star-forming regions called cosmic seeds. As reported in a Harvard-Smithsonian Center of Astrophysics press release, the seeds generally weigh between 5 and 25 times the mass of the Sun. Previous theories proposed that high-mass stars form within the very massive, isolated cores weighing at least 100 times the mass of the Sun. These new results show that that is not the case. The data also demonstrate that massive stars aren't born alone, but in groups. The team also was surprised to find that these two nebular patches had fragmented into individual star seeds so early in the star formation process. They detected bipolar outflows and other signs of active, ongoing star formation. Everything I've just described only supports the electrical theory of star formation. The electromagnetic Z-pinch, overwhelmingly more powerful than gravity, works far more efficiently and rapidly than gravity at pulling in material to form a star or planet. Moreover, the grouping and doubling of stars is a predictable effect in the electrical theory of star formation. Plasma cosmology predicted that stars would form along filaments like beads on a string. And the surprising number of binary stars observed in the Milky Way galaxy becomes predictable when we consider the experimentally verified doubling effect, characteristic of electrical discharge. For extensive background on this, I recommend viewers visit Wal Thornhill's classic space news, Seeing Double. In the filamentary networks where stars form, the electric universe proposes that so-called hot Jupiters can easily form along these same lightning channels. Countless puzzling exoplanetary systems, including exoplanets with retrograde orbits, which is orbits in the opposite direction of the spin of their parent stars, may also affirm another aspect of the electric universe theory as proposed by Thornhill. That is, that the gravitational force is modified by the electrical nature of any body, so that if a body is charged more or less than those around it, there will be charge exchange, and in the process, gravity will modify the orbits of those bodies. The result is that planetary capture is far more likely in the electric universe than in standard cosmology. Along these lines, consider the following extraordinary revelation into the formation of so-called brown dwarf stars. Recently, a team of astronomers using the James Webb Space Telescope has undertaken the task of identifying the smallest of all observable stars. They focused their attention on the Perseus star-forming region about 1,000 light-years away, at the center of the star cluster IC348. The team identified 3 so-called sub-brown dwarfs, the smallest of which has an estimated mass equivalent to 3 or 4 Jupiters. It is that star that is said to be so unusual it defies all conventional explanation. A Science Alert report describes the conundrum as follows. This is a real puzzle. For star formation, a cloud has a lot of mass, and therefore a lot of gravity. Producing something the size of a planet would start with a smaller cloud, and therefore less gravity, which means the formation process is a lot more arduous, the researchers say. It's possible that the objects are exoplanets that got booted out of their planetary systems, but this is also unlikely. As far as planets go, they are quite large, but most of the stars in IC 348 are very small. The formation of large planets around small stars is also difficult to explain. Moreover, the cluster is very young. There hasn't been enough time for planets to form and get ejected so far from their systems. The discovery of so-called brown dwarfs, whose very existence is gravitationally impossible, is not surprising from the electric universe perspective. In his 2008 article, NASA's Dim View of Stars, Wall explained brown dwarfs in light of the electrical theory of star formation. He wrote, "In an electric universe, there is no such thing as a failed star. They have no thermonuclear engine to fail. All bodies in the galaxy receive external electrical energy from the galactic circuit. All stars are an electrical phenomenon. There are no misfits in an electric universe. All of the assumptions being heaped upon the meager photons received from deep space merely serve, as usual, to force-fit the data to the standard model of stars. The very name, brown dwarf, assumes that these stars are, quote, compact balls of gas floating freely in space. In stark comparison, the electric model describes them as huge, because the light from a star is a plasma discharge phenomenon, with only a loose relationship to the physical size of the star, and a strong dependence on the electrical environment. Brown dwarfs do not simply cool down over time and wink out. They are externally powered electric lights. In December of 1999, Wall also wrote of so-called brown dwarfs. The apparent size and color of an electric star is an electrical phenomenon. If Jupiter's magnetosphere were lit up, it would appear the size of the full moon. The light of a red star is due to the distended anode glow of an electrically low-stress star. Red giants are a more visible and scaled-up example of what an L-type brown dwarf star might look like close up. My prediction for 2024, and indeed for the rest of the decade and the foreseeable future beyond, is that the number of, quote, impossible planets and stars will continue to grow in direct proportion to our technological ability to detect them. And as always, the so-called impossible objects will be deemed as such because their very existence cannot be explained gravitationally. Meanwhile, a new and rational pathway offered by plasma cosmology and the electric universe continues to await astronomers' consideration.